All right. All right, let's get started. So, I haven't graded the exams yet. There's the two girls in the audience are going to take it today because of Grace Hopper. And after that, it should be out by Wednesday, the results. Any questions on the homework, which is due tomorrow, I believe? A lot of questions on the homework.
When you're using, so if I fork and say I want to do the command ls pipe grab something, right? And I fork, and the parent becomes ls, and then the child becomes grep, like recursively calls, call grep. I want to wait after I call ls, or because I feel like if I don't call grep first, ls is going to be writing to the pipe, but then where's it going to go if grep's not reading it? Right?
Yeah, that's actually not a problem. So it's okay to write into a pipe even if no one's reading. Either if you write a lot, then your program will stop. If you write a little, your program might finish, but the stuff is going to go into the pipe and then come out the other end. Okay. So you should be okay.
So I want to wait after ls though, or?
You want to make sure you're. So I think I recommended in Piazza to fork even in main, like when you get the command, start by forking right away, and then in there you might want to wait for all the child processes to finish. Okay. You don't really need the child processes to wait for each other because they have this dependency through the pipe, so they should be okay anyway.
Yeah, because it works when I don't wait, but then if I try waiting, grab hangs or something. So I don't know. I probably have something else wrong. I'm trying to do it the way you implemented it. The parent becoming the thing and then recursively call with the rest of the string.
Yeah, so that makes sense, I think. Yeah, everything gets much easier if you put your first fork call in main, I think. Okay, right. Just so that whatever happens after that, you don't care what happens to the processes. Like they can all go and die, right? And your shell remains at main, basically. Okay, so we are done with chapter 10, I believe, which is input-output sort of stuff. And now we're going to move on to networking. This is not going to be as in-depth, of course, as CS450, but we'll grab a little bit of what used to be the introduction to CS450. We'll put that here, and then 450 will become a little more advanced. So, let's see. But I believe, I haven't really agreed with Tim yet, but I believe the next homework is not going to be on networking, it's going to be debugger. So that gives us a little bit of time to get started with networking before we do our first networking homework. There's probably only going to be one networking homework here, actually. But this should be a fun lecture, because I thought we'd do a dive through the whole networking stack to see what's going on when we download a web page, basically. So let's take a browser. We'll go to our favorite website.
Not Reddit?
Actually, Reddit is, I put it in my hosts file. Yeah, I can't actually get to Reddit. It's a little bit too addictive, so...
How do you do that? Can you teach me?
Okay, I'll show you that. In preparation for the
because I need to do that.
Exams later this semester.
Seriously, I need to do that.
Here's what I have in my Etsy hosts file. On Windows, there's also a host file. It's not in Etsy, it's somewhere else. So here, I redirect all of these names, things that I should not be go visiting too often, to this, 127.0.0.1. Any idea what that is? That's a local machine. And I don't even run a web server on my local machine, so it's not going to work out. One is a name and the other one is an IP address. And we'll see the difference, like how that all fits together today as well. So let's go to a website that is also very good but doesn't publish new things as often. The Oatmeal. I thought there was a particular one. Oh yeah. So this was the one I happened to look at this morning. So that nice web page. I hope everyone has tried this at some point. So everyone's familiar with HTML, right? Okay. So Yeah, that's a comment. This guy is great. Anyway, so here's the real stuff. So the first level, and maybe we'll do this in notes at the same time. Call it the networking stack for web browsing. So it actually looks the same almost the whole way down, but we'll start for the web. So for the web, we're starting with HTML. It's not really networking, right? This is more of the real application, but since it's what everyone thinks is the internet, let's start with that. Okay, so you know all these hyperlinks and so on. I won't bore you with that. What happens next is, of course, we have to get this from somewhere. So how do we get it from somewhere? Well, we connect to a web server. The web server is called the oatmeal.com. So how are you able to connect to a web server called oatmeal.com? That's a tricky thing in the first place. As we'll see later on, all the computers, all they have are IP addresses. If you know the IP address of a computer on the internet, and it's a public IP address, let's not go into the details, you can reach that machine by sending a packet to it. You write a little packet, it's like a letter. You put sort of the address on the outside, and the rest of the system will deliver the packet to the other end. So that's good. But you can't give it names. There's no room for names in these packets. So if we want to send a packet somewhere, we first have to figure out who or what is their address. So this is their name. Now we need their address. One way you can do it is you just type in host, and there comes, so there's a couple of things coming up, but this is really what's important here, the IP address. That's the IPv4 IP address, and it looks like it doesn't actually have an IPv6 address. Okay, so now we are able to contact this machine if we send a packet to this address. The problem with these packets, the internet was actually built for sort of the lowest common denominator. There are all sorts of different networks. Internet stands for inter-network, right? So there were all these different networks starting out. They were all working different ways. There was some phone network, there were some serial cables, there were some wireless links, wireless packet radio links, a little bit of everything. And they didn't all support fancy features. But one thing that they could all do was deliver a little bit of data sometimes. Okay, so the internet was built, the rest of the internet stack was built to accommodate any sort of link under. Put them all together into one big family. Right? The problem then is that now you have to, you have almost nothing to rely on, except the fact that they can sometimes deliver a little bit of data. Okay, so what we do is we send little bits of packet, a little bit of data, that's up to 1500 bytes in one chunk. We put the address on there, we give it to the network, and then it goes over a bunch of links. That's 450 material there. Goes over a bunch of links. This packet hopefully makes it to the other end. It's not clear. Sometimes it doesn't. Maybe 1 out of 100 packets or so you'll find doesn't make it, if you're unlucky. Okay, so then what? Now we have to see if, oh, did they get the packet? So they have to send us a packet back to say, yeah, I got it. All right. If they got the first one, we can send them another one. This seems like a big pain, right? And actually, sometimes the response gets lost. Other times you send 2 packets and they don't arrive in the same order because they went different ways. There's all sorts of stuff going on. So this is a very common problem for all different internet applications. Therefore, the operating system provides a service that takes care of it. It's called TCP, or if you want, a streaming connection. So here, we actually pretend that the internet works like a file. So we make a socket, then we get a file descriptor back. Now we have a file descriptor, we can tell it who it should be talking to, and after that it works like a file. You can read from it, you can write to it, and it always takes care of everything else. That's a big part of 450. How do you make it, over this crappy network, how do you make it actually communicate reliably and in order with the other end, and quickly? Okay, so we have this IP address, and then we connect to that server. So let's try that out. So Telnet uses this service. It's called TCP is the service, but Telnet is a very basic application that just establishes a connection to the other end using TCP. You tell it what port. That's like on a letter that might be which person in the household. Right? You have the address to the household, and the port says which person. The port is really which application. Port 80 is the web server application. So let's try that. So we'll talk to that machine, and we'll say port 80 because I want to talk to the web server on that machine. Okay. Okay, so apparently OAuth-VIP gpdatacenter.com, that's a different name for the same address. So every address can have as many names as it wants. And now I'll talk some HTTP to it. It's a very simple protocol. Let's start with the basics. I just want the root page. Okay, that doesn't look like the oatmeal at all. Let's try this out. Okay. So what happened here? I got a response. I sent my request. This is too simple a request. The server doesn't actually understand what I wanted really, because this server probably hosts several different websites. Okay, so I sent a simple request and it says, yeah, okay, fine. And then it responds with some other parameters or some response headers saying, oh yeah, okay, we got HTML text coming, right? It's a certain size, 844 bytes, some other stuff that's not too important. Okay, and then comes the data. There's an empty line, and then comes the data. And it looks like it's HTML. It's pretty good. All right, let's try getting the same thing using the web browser. So now I'm not providing a host name. So the web browser, if I put it, let me make a new. Okay, so that's what it looks like if I just talk directly to the server. So the server doesn't, so the reason for this is probably that this server serves lots of other websites too. It's one machine. It has lots of different websites depending on what name you use to refer to the server. Okay, but we just said you can't send names in these packets. So how does that work? Well, at the application layer where we're sending the actual request, we can type whatever we want. So let's try that again. And I'll say get, what was it? Comics house. It's still not going to work if I type this out the same way. But now I'll specify host the oatmeal.com. So now I'm giving the server a hint here that, okay, I'm actually wanting to talk to the oatmeal web server here. And now I got my pterodactyl up here somewhere. There he is. Okay. So I had to specify, I had to tell it who I actually wanted to talk to from the TCP connection, or the file handle if you want. There was no way for the web server to tell what was going on here. But if I told it explicitly what I exactly want, then it's fine. So here you can actually assemble this if you want, right? The oatmeal.com/comics/house, and then that's the URL. Okay, questions so far? This is just HTML here. That's not interesting. Okay, so we're ignoring a few details here, right? How do we connect to this server? In terms of code, we'll probably look at that probably next time. But the basic idea is we tell the OS, oh, I want a reliable in-order connection to this other end, and after that, you can write to it with just write, just like you would to a file. You can read from it with read. There's actually a couple other function calls called send and receive, but they do the same thing. Okay, so it feels like another file handle. But how did that all work? Let's go a little bit deeper. So now, so far I should type this out. So HTML, just application content. And that's not a protocol, this is a standard, I suppose. And then we were talking HTTP. So this was Hypertext Transfer Protocol. I guess there's the, like that. Okay, so we were using port 80, but that's not important. This is sort of a convention. if you contact a machine at a certain port, if it's a port under the number 1024, there's some convention as to what applications run on this port. So the application web server runs on port 80. There might be a application email server running on the same machine, in which case it would be port 25. So we can try it. See if we can talk to the email server. No, there's no one listening on that port. So we're not getting a response. Okay, port 80. So this is, we send a text request, get a text response. Pretty straightforward. Okay, so this text request, yeah.
Is there anything special about services under HTTP server on 8080 instead of 80?
So anything special about other ports than 80? So you may have seen sometimes port 8080. You may have seen 9090 as well, 8888. There's no difference. You can run your web server on any port you like. But the problem becomes if you run it on port 8080. Now you try to go to, actually let's see if there's anyone listening on 8080. No one listening there either. Now you have to specify which port with a colon here. If you use 80, a web browser knows, okay, I'll go to port 80. It's doing that by default. If you're not using 80, then you have to specify which port you want to talk to. Okay, there's something special about any number being over 1024. If you're a regular user on a machine, you can't run an application that takes over that port. You have to be a super user to use that port. Everything else is the same. Okay, maybe I should point out one more thing. Only one program on one machine can listen to one port. Right? So this port 80, it's taken by the web server. No one else can come listen to that port. So this is the only significance of these numbers is how you find them. Right? I want to talk to some application on this machine. You don't say HTTP. You can imagine that too. You can imagine sending a message to the OS on the other side, which specifies in text which protocol is it you are expecting to talk. Right? And that might be helpful. You could imagine saying even the process ID that you want to talk to on the other end, but how would you know the process ID? That's sort of randomly assigned here. So it's just a convention for how to reach the other end. Okay, so the next level down. So HTML is transferred using HTTP. These HTTP requests and responses, they are transferred in turn using TCP, Transmission Control Protocol, which provides reliable delivery over an unreliable link, in order delivery, and congestion control, which we can skip for now. Okay, so we want to send our request. Now it's going to get a little bit more difficult. So we actually use TCP with Telnet here, but let's see how TCP actually works under the covers. So in order to do that, we need to use some other tools. So I'll use TCP dump, which is sort of a misnomer because TCP dump doesn't just dump TCP, it dumps all sorts of stuff. So let's try here. So I'm saying on my network interface 3, that's this one I'm plugged in here. And I'll say very verbose, print out everything, the first 1500 bytes, but only port 80. Because otherwise, actually, let's try without first, see what happens. Okay, there's some stuff happening here in the link. It's not a very chatty link. So now I'm listening for everything that's happening on my Ethernet cable here. Anyone else on the local network would be sending messages like this. There isn't much going on. Let me try reloading this page here. Oh. You want to see it at the same time, of course. Then there should be a little bit more happening. Oh, interface went down. What now? Let me see. Maybe. Oh. Did it change names on me or what? Huh. Okay, well, it looks like the wire stopped working, but the wireless is up now, so we can use that instead. It's a different port here. See what's going on. Okay, there's some crap being transmitted here. Someone, Amr Abdallah in the library is sending stuff. It's a little bit of everything. Okay, let's try.
What is this?
This is stuff going over the wireless. So I guess
This wireless?
we were kind of close to the library, so maybe we overheard something from the library. So this is wireless transmissions in the neighborhood that my laptop is picking up, and I told it to listen to anything. So there apparently isn't much going on. Usually there will be much more in on a typical machine. Oh, but yeah, okay, it's not everything. It's not everything that's going on in the wireless. I didn't tell it to be very aggressive in what it's picking up. Okay, so I'm reloading this. I was hoping we would get. Yeah, okay, it's just a little bit delayed, but there's a lot of stuff going through here. Okay.
You're hoping to get the pterodactyl again?
No, it actually, it might be in there.
Probably not. If you didn't refresh, it probably did. Have you updated recently?
No, I don't think so. Well, anyway, we can try it with the. Where's the pterodactyl? He might not be in there. Anyway, so there's a lot of junk. Okay, that's a start, but let's take a closer look here. So in order to do that, I suggest we not listen to everything because it's just too much at the same time. So let's kill off a little bit of this. Oh, that was the last of it, I think. And we'll, hey. Oh. Ah. What? Okay, we need a different window. Where are you? Oh, look, there's two of them. Okay, well, they will die. With the -9, that's non-maskable, right? So we should be able to get rid of them. Okay. We're good. Okay. So that was a little too much stuff going on there. So we'll just say port 80 and host, and now this is a shortcut, but I'll say the oatmeal.com. So TCP dump is nice enough to do the translation for me. So there's a whole system, whole worldwide domain name system with lots of servers and so on that gets involved with translating this name into IP addresses, and that's something you'll see in 450 as well. In fact, you'll make a program that does the resolution manually. It's a very good homework. Okay, so now we're talking to just the oatmeal, or just listening for communication with the oatmeal. Let's see what's coming out. Okay, there it is. This was our entire communication. Ah, very good. Very good. So, looks like my browser here said, oh, let's see what's going on. Too much. Let me clean this, clear this out, and we'll do it again. So we can scroll back without confusing things. Alright, let's do this one more time. Okay, there's the entire communication. So there's quite a bit going on there. Maybe no pterodactyl though. Okay, so here, every one of these lines, every one of these chunks represents one packet, either sent or received. So here I started out, my TCP here started out sending a packet to, from UIC.edu to the data center, port HTTP. That's just a nicely written out 80 there. And it's saying, okay, please establish a connection for me to the other end. And then it looks like we sent another one. Maybe the first one was lost. Because this one is identical. It's yet.
No, it's 72. The number is different.
Yeah. Oh, it's actually established more than one connection. Oh, that's a little dull. Maybe there's too much going on, and even in this one here. So let me do a manual connection. So we'll clear this out again. There's so many images and things in the browser that it kind of gets crazy. So let's just look at a single communication here. Now we should be able to see pretty clearly what's happening. All right. So I established my connection. I haven't said anything yet. So our first message here says, okay, please, from wireless, from UIC to data center, please establish, that S here means actually establish the connection. Then comes a message back from the data, from O2VIP here to UIC saying, yeah, okay, we're establishing a connection here, and this little period here is acknowledging that I wanted to start it. So that's sort of just coming back. And then I send another message back to O2VIP. Any idea why I would want to send yet another message? What's the idea?
Talk to you using this port.
No, this is actually, it starts already over here. There's a port over there, you can't see it. In fact, we can do it with, it's easier with the names, easier to see what's going on than with IP addresses. Yeah, okay, so here's my transmission, now we closed it. We probably ought to get another one here. We did, didn't we? Yeah. Yeah. Okay, so but let's look back again here. So here's me sending a request. Let's connect. Here's another one saying, yeah, okay. And here's some other message from me. This was before I typed anything. Why would I want to send one more message? In fact, look at the length. It's really short. 0 bytes. I didn't actually send any data payload. There's yet another message going from. Almost that. So it's saying, okay, so first I sent a message out saying I want to connect. The other guy says, yeah, okay, I hear you. Let's connect. But now he actually needs to know that I got his message. Right? If he doesn't know that I got his message, the message might have been lost. And now nothing starts. So he actually has to, so I have to send another message back saying, yeah, I heard you. Right? If I don't send this message, he will eventually send yet another one. Right? Keep sending the other one until you get the ACK back. So that's how the reliable transfer works. Okay, and then unfortunately I was too slow. So now we got something else going on here. Now O2VIP got sick of me, and they say, finish this connection. And I say, yeah, okay, fine. And then, yeah, okay, I heard you, right, from the other end. And then there's yet another one here. And now we're done. Actually, no, I sent 2 messages. First I sent a message saying, yeah, I heard you. And then I say, yeah, okay, let's finish from my end too. Turns out there's a bidirectional connection. You can close half of it if you want. And then finally, the final piece here, the O2VIP says that they heard that we also want to close it. So now we're done. Okay, so there's all these packets are being sent sort of under the covers. The web browser doesn't have to care. They just say, type in the code is just connect and shut down.
So the fact that the oatmeal is sending back to you more than once, and you don't say that you received it, that's all TCP, right?
That's TCP, yeah.
That's how it creates a reliable connection.
Yeah, exactly, yeah. So there's 2 things here that makes a TCP make a reliable connection. The first one is this, the acknowledgements. So this is a clean acknowledgement with nothing else in it. I just say, okay, I got your finish request here. There's one more piece to it. There's a sequence number. So here we're acknowledging, yeah, okay, I got the previous one, now I want the next one. That's the acknowledgement part. Then there's also a sequence number saying, okay, this is the second message, the third message I send you, something like this. And so if you have, so here you see one message, sequence 2, there's a sequence 1, there's a sequence 0. If you send multiple messages and they arrive out of order, the OS isn't going to deliver it, or TCP isn't going to deliver it to your application until they have the right one, so they can sort them first. So you always get them in the right order.
Because the acknowledgement has to happen on both sides. Right?
Oh yeah, yeah.
So how do you define how fast you send stuff?
Ah, good point. Yeah. So how fast should you retransmit, and also how fast should you transmit in general? If you have a lot to transmit, you can only send a kilobyte or so in a packet. How fast should you be sending them?
How long do they have to wait?
Right. So okay. So there's two intervals here. What's the retransmission interval? How long do I wait until before I get an ACK, or before I retransmit? And then the other one is between my packets. How long should I wait until I send another one? Because we might overwhelm the network. If we send too many, things get too busy, all my packets are going to get lost, other people will lose packets, it's not good. Okay, so those are both things that TCP is highly tuned to do right. And it's not trivial, because it all depends on what the links are like. If you're TCPing with the moon, which is entirely possible, you're going to have a very long round trip time. But it's, what is it? I don't remember. But it's probably on the order of a second, or maybe a couple seconds. Anyone know? How long to the moon? Okay, this is
I believe Mars is like 5 minutes or something.
Mars varies a lot. It can be up to 25 minutes when it's on the other side of the sun. Right? But the moon is pretty close all the time. Anyway, so you divide by the speed of light, and there's your round trip time. But that's something we do in 450 as well. Also, finding out how long you should be waiting for these ACKs is something that we do in 450. We implement a reliable transport protocol over this broken link, which is the internet. Right? And also this last part, the interval between transmissions, that's called congestion control. It's crucially important to the whole internet. The internet wouldn't work if TCP didn't have congestion control, because most applications that we use, they can pile in tons of data at the same time. They can send arbitrary amounts, and then most of it wouldn't get through, but you would use a lot of links along the way. You use up all that capacity, and then on the very last link, your grandma's got a slow link to her home PC, you know, that you're Skyping with. There, she's losing the packet, right? So now you use everyone's links along the way, and finally you lose the packet at the very end. It's a total waste of energy for everyone. So what TCP does is also figure out how fast can I transmit given current conditions. It's another thing that it does under the covers. Okay, but this isn't quite enough. Right, so far let's fill this in here. So TCP is not able to actually deliver anything. Right? TCP is just, it runs on my machine, it runs on the receiver end, it doesn't run anywhere else. So there's a TCP implementation here, there's one on the server, and we have a conversation. If we lose a packet, we send another packet, we kind of make up for the losses and so on. But how do we get the packet to the other end in the first place? So TCP relies on yet another underlying service, which is called IP, or the Internet Protocol. And the Internet Protocol is just that, an inter-network protocol. So it's actually, again, it's only a way for networks to talk to each other. It doesn't give you any communication within a network. So, but let's start with the Internet Protocol here. If you have an IP address, which we have, you can put that in a packet, and then let's run this again, but now we'll run it with -n. We'll see the actual numbers. So I'll make the connection again. Okay, so now we see this is my IP address. That's the port that I used as a source port. I have a source port because if I want to have a response, they need to be able to know who to send it to. So I advertise here, responses go to this port. Okay, so and it goes to this machine. The first 4 octets here are the IP address, and then the 80 at the end says which application at the end, and that's the web server, right? Okay, so within IP, so maybe we should draw this. The whole thing is a big stack of, they're not round unfortunately, so we'll make square things. They're more square than round, although you never know with bytes. Okay, so at the, we'll start with the bottom. Here we have a bunch of HTML. That's what we wanted to send, right? My application payload. Okay, never mind. My application payload starts here. Okay, so now I wanted to, if it's a web application, that is. So I want to transmit that. Of course, to talk to a web server, I need to know what protocol to talk to a web server, so that was HTTP. So here I started with, let's say this was maybe 1400 bytes. Up to 1400 bytes, I can put in a chunk. And then we have some HTTP header. It's probably going to be a little less than this, actually. Let's make it 1200. So before those data bytes I sent, I have to put an HTTP header with some, so call that maybe another 100 bytes. With that request, right? Or in this case, this is not the request, this is the response, because we got actual HTML coming back. Okay, so on top of that, hello. Doesn't want to collaborate. Okay. So now I'm sending. This is a character array at 1200 bytes. Now I have to make the array a little bigger. So before I prepend 100 bytes of HTTP header in my transmission, but this is not necessarily. You don't need it if it's a very large payload. That's going to be many TCP packets full of data then. Okay, and then for every HTTP transmission packet block, there has to be a TCP header now, because we're using TCP. So that's going to be another 32 bytes or so. Or actually, maybe it's 20 bytes. I think it might be 20 bytes. So there's a TCP header there that says which port do we go to. A sequence number is in there. There's an acknowledgement number. There's some other flags, stuff like that. Okay, but TCP now takes all of this. This is now a larger array here, and it needs to say where is it going, right? So for that, we need yet another one. Now we have an IP header. So we prepend an IP header. I think that's 20 bytes as well. I have to think about that. But so in the IP header, we say, oh, what's the destination address? And we also say our address, like you write on the back on the envelope, or up in the corner there. You say, like who sent the letter. Same thing here. We have to say where it came from, so that the receiver can respond. Okay, so now it says where which IP address do we want to talk to? That's pretty good. But unfortunately, the local network, my Ethernet cable, which is broken, or my Wi-Fi connection here, they don't know about IP. So the Internet Protocol was built to accommodate all these existing different networks and make one big one, right? All the different networks in the world, try to make one big one where everyone can talk to everyone. So unfortunately, that means you have all these legacy networks and they don't care about IP. They don't even know what IP is. So all the service that they provide is, I can take a chunk of data and I can deliver it to anyone else inside of my network. Okay, so now the very last hop here. Here we have the Internet Protocol routes packets to any IP destination worldwide. IP then relies on I'll call it link. link layer. That's the local network. All it does is deliver packets to any destination on the local network. Okay, so can anyone name a link layer? Wi-Fi is one. So Wi-Fi, all it can do is get my packet from here to, there isn't one in here, but one of these access points that you see around. The packet goes using Wi-Fi to there, but then we don't know. There's maybe an Ethernet connection, that's the cable, right? Ethernet connection going from the Wi-Fi access point to some local switch in the building. And then you might have a fiber, which is not Ethernet or Wi-Fi. That's probably, it could be Ethernet, it could be SONET. There's a fiber going from there to ACCC's central router. And from there, there's probably another fiber going out to, I don't know, level 3 or some internet provider. And then there's another one, right? So you have all these different links of all different types that use different link layers. So what happens here is at the very top, and now this is almost where things get serious. So here's the link header, and that says MAC address destination, or say local destination. Okay, so the size varies a little bit depending on what type you have. Okay, and then finally, unfortunately, this is still just bits. How do we get bits from here to over there? Anyone? Radio, right? So radio waves don't transmit bits. They're just waves. So we need one more piece here. So this is all of the bits that we're transmitting usually, but so now we've decided, like, oh, who do we want to contact locally? It'll be my Wi-Fi access point. Right? So I have to transmit a radio message that starts saying, oh yeah, local Wi-Fi access point, hear me now. Right? It'll pick up the message, it'll read the IP header, and it says, okay, that's going out to the internet. Let me send it out that way. Right? And everyone along the way looks at the same thing. You have different link headers. Sometimes Ethernet, sometimes something optical, sometimes another Wi-Fi. They're all looking at this, they see, oh yeah, that's for me. Then they look at the IP header, and they see, huh, yeah, that's going sort of in that direction. Let me send it to this guy. Okay. Next guy does the same thing, yeah.
These things don't collide.
They don't, they can collide over the wireless. And if so, you have a packet loss, and you have to deal with it. So some radio links deal with it locally, so they retransmit. Other ones rely on TCP doing it. Okay, so the routing here, it sounds fancy. It really works sort of like the post office again. So this guy comes to your door, all right, and so there's a letter on there and it says, okay, this should go to Sweden. And it says some other things too, but he doesn't care. He just says, okay, Sweden, main office. Right. So he'll give it to the main office. Guy at the main office looks at the envelope and says, oh, Sweden, fine, downtown. Right, or O'Hare. Give it to O'Hare, whatever. Because it's not here. So it's got to go to O'Hare. So it goes to O'Hare. O'Hare guy says, oh, Sweden. Actually, it would probably say Europe too. In the IP case, it would probably say Sweden, Europe. It says Europe, okay. Plane to Europe, whatever Europe destination. It gets to Europe, then they say, oh, Europe, yeah, we're in Europe. Sweden, oh, okay, that way. Goes to Sweden, and once it's in Sweden, it says, Stockholm. All right, that way, right? So it's all little pieces along the way, and they're all making their own decisions. At some point, it goes to my dad's mail carrier, who says, oh, that address, I know where that is. So he walks over and puts it there. Right? Exact same thing with the internet.
What would happen if one of those routers says, the thing that you just sent me actually has to go back to you?
Yeah, that happens sometimes. Sometimes they disagree, so they say, okay, you should have it. No, you should have it. No, you should have it. And it goes back and forth. And then after 255 times around there, they say, okay, we've done this for a while, and they throw the packet away. There's a TTL in there that limits this. Yeah.
And if the packet gets lost?
do you have to send it all the way, like from the beginning address?
Oh yeah. So if anyone along the way drops the packet, makes a mess, then you have eventually you notice, you figure out how long you should wait to get the next message back. If you don't get an ACK, then you just have to retransmit from the beginning again. There's no memory anywhere in the system. Okay, so one reason why there's no memory along the way is that you have all these different pieces. They need to be cheap. They need to be really simple, and they also need all this stuff needs to work with old crap that's been around since the 70s. It's not just all the modern things. Everything is on the internet since when they started. Okay, so let's take a look at the link header too. I'm using TCP dump here because I find it instructive to see a piece at a time, but we'll also use Wireshark briefly, which is a nice graphical illustration. So here, if I specify -E, now we'll see the Ethernet header as well. I'll make the same, I'm not actually going to talk to it, I'll just connect and not say anything. So now we have the Ethernet header as well. You'll notice here. So in the first request coming out, it says, here's the IP address, right? The same thing. I'm talking to the oatmeal. But here is the Ethernet header now that we're showing as well. So that's my my Ethernet address. You've seen these MAC addresses before, I'm sure. And which address is this then?
Theirs.
Whose?
Or the router that's
That's the access point, yeah. Whoever talks radio that I want to reach. So now it says, okay, radio access point over there, you pick this up. Because there's a lot of people that could pick this up. And they don't know if it's for them or not. So I have to put an address there so that they know it's for them. Okay, and once they get it, then they throw this away. Like they see, oh, it was for me, okay. The rest is not important. Throw away this blue part here. Look at the next part and see, where's it going? Right? And now it needs to go somewhere in that direction, which means now you've got to figure out which link header to put on top next so that you can get to ACCC. Right. Okay, so in the last couple of minutes, let's try this with Wireshark, which is much prettier. Let's see, how do we clear this? I guess we can't. That's okay. I'll just... Okay, so now I'm capturing all TCP again. We'll do the same thing one more time. Actually, maybe this time I'll... What was it? Comics House. Okay. So this is all the stuff that happened for this one fetching the HTML. Let's see, let's filter this here. Port 80 and host. Oh no. Okay, let me close my browser. I think my browser got a little trigger happy there. It decided to go fetch something, and I'll close my email program too. And Skype. Anything else? iTunes. Because they all just get online anytime they feel like it. My calendar too. Okay, let's try this again. Stop. Go. Oh, now I got the root. I didn't get that particular comic, but I think it's bad request. Lame. We don't have time. So we'll look at this anyway. So here's my here's the beginning, the SYN that we looked at. Yeah, let's start a connection, right? Every line here is one transmission. Let's see what we can do. Yeah. Yeah, it stands for synchronize, yeah. So here's that stack we talked about. Right? Actually, it doesn't show HTTP here because there isn't any HTTP yet. We're just saying, yeah, connect. There's no HTTP conversation. If we go a little further, hopefully we'll get getting some. There's some HTTP. Okay. So that was my request, right, at the very bottom. Then we have a bit of TCP. This is all the data in the TCP transmission. If I just select this, we can see it actually up down here. We can see in hex how much it is. So that's my request. That's the TCP, the entire TCP, including. No. Why doesn't it show everything? I'm not sure. Okay, so there's the. That's too long. Anyway, so we can see every part here. How much it is. I'm not sure why it was so long. Here's our IP header, right? Which port and so on. And then comes the link header, and this is the entire thing. I don't know why this didn't show up right. Anyway, so there's the entire networking stack. And next time, maybe Tim will be talking about debuggers, but at least time after that, we'll be doing a little bit of network programming on our own. All right? So I'll see you Wednesday.
Everything from the debugging homework we already covered, right?
Yes. Well, or Tim will cover some of it.
Okay. Well, we're going to stick with this.